So for this example is this, we have the hinged rigid beam. And this and attached to a spring and anchor. And this one, this theta is the equilibriums we use to measure. And also this end is under force excitations, and the force is something like this. Okay, so that's periodic, and so this is 0, and this is t. So basically, these have a period t. And this beam has a mass n and has a length L. Okay, but it's rigid, so there's no spring constant. So for this case, we want to determine the steady state response of theta t. Okay, so steady state response. So the first one we need to formulate is the equations. So that's the first step. So here we plot the free body diagrams on the initial component, so which is the beam. And here for our linear vibrations, we assume the theta is small. And that is our fundamental assumption. We assume small vibrations. In this way, we can pretty much, in the good approximations of the system into linear systems. Okay, so here we usually, for drawing, we exaggerate, but usually the theta should be small. Under that situation, and for this case, this one is under a few kinds of force. One is the spring force, and that is K times the distance from here to here, assuming theta is small, so basically that distance is almost L times theta. And assuming this one is equilibrium is at the vertical configurations, if we swing to the right a little bit, and assuming theta is small, basically you can approximate this distance is about L theta or L sine theta. But L sine theta approximate basically is L theta when theta is very small. Okay, so that's the reason why we assuming small oscillation. Otherwise, we have to deal with nonlinear vibration, which is not on the topic here. Okay, so in the similar way, the force from damper is L times velocity, L theta double dot. And also, in addition to this one, we have an externally applied loading, which is Ft. Okay, so that is the total force applied to this and to produce a motion, which is a swing. So basically, the forces will produce a corresponding moment to make the motion that is around this pivot here. Okay, so basically, this one is equivalent to, this is I. Let me call this pivot is point O. Okay. I O theta double dot. Good. Okay. So basically here in terms of the formulation is this. We take the moment about the pivot point O and say let me take the sign conventions along with our adopted direction of the degree of freedom, so that's a counterclockwise. Let me take that as a positive. So that one must be equal to I-O theta double dot. Okay. So in this way we can see what is the moment. So the moment will be contributed by three forces. So one is K L theta, that is a force. And assuming this is a small oscillation, just pretty much assuming this angle is small, so that force you pretty much can multiply with L directly without considering projection of sine or cosine. Okay, so here multiply with L. So with this case, this is a moment, and this moment from this force producing its clockwise direction. And per our sign convention, so that should be negative here. Okay, and then the second moment, the moment from the second force is this one, the C, the damping force. So that damping force is C L theta dot. And again, the force multiplied with the arm, and that is L. And that's the moment contributed by this force, which again is clockwise. And so per our sign convention, that is negative. Okay, and then the third one is, yeah, I think here okay. So again, F is a force and multiply with L, and this is the moment contributed by this externally applied force, and that producing counterclockwise moment. So here is positive. So the whole thing is equal to IO theta double dot. And what is IO for this one? The IO of the straight beam about the pivot point here is equal to I about its center of the moment, the centroid. Okay, so centroid plus the mass multiplied with the distance from the centroid to pivot point. So that is the formula here. And what is this centroid? This one, you can check it from dynamics. That is 112 mL squared. Okay. So this one is from the tables from dynamics. And this one simply we apply the parallel axis theory. Okay, so again, what is the L over 2? That is the distance between the centroid to wherever the pivoting about. Okay, so that is this one. So basically this one we have everything plugged in, so that is M L squared divided by 3 theta double dot. Okay? So with this everything in mind, then we have this information. So let me say that is M L squared 3 theta double dot plus C L squared theta dot plus K L squared theta and equal to F T times L. Okay. So with this one, we can further simplify. So for example, let me divide the both hand sides by L. So 3M L theta double dot plus C L theta dot plus K L theta equal to F of T. So this is a typical dynamic systems, and let me redefine because we want to plug in the template from whatever the formula we have. So how about this? Let me define the coefficient and with some symbols. So let me say this is ME plus CE plus KE equal to FT. Okay, so basically that becomes the MC, the mass damper spring constant system subject to this one. Okay, so for F of T, this one first we can using Fourier series expansions to decompose. So F of T from our tables for this kind, and let me write it out the information here. F0. So let me say this magnitude. This magnitude is F0. So this magnitude is F0. Okay, so the pulse has a magnitude F0. So with this information, we can decompose the, since it's F0 divided by 2 and plus 2F0 pi cosine omega t plus 2F0 3 pi cosine omega 3 omega t and plus etc. So basically that is 2F divided by odd number pi. And for cosine omega, cosine 3 omega t, cosine 5 omega t, 7 omega t, etc., etc. Okay? So here I only pick up the first three terms. So maybe I can pick right for another terms here. So 5 pi cosine 5 omega t. Okay? So with these things ready, then we can begin to write it up the response.
Did I miss something? Or was there supposed to be a theta with the f of t times L? No.
Questions?
Yeah. It must be one. So it's the first time. Right. And this is theta times L, right?
Double check with this one. Okay. And double check with this one. But anyhow, assume if the Fourier expansion of the force is become like this one. Okay, assume that one. And then here I opened up our template. So basically this is our systems, NE, CE, and KE. And under different the terms, and right now we know the terms is actually there. And that is the template. Okay, so keep this in mind. Then we can begin to write it up. So theta, steady state, and that is response of the system. This system respect to the individual terms here. So for example, let me call this called the term 1, and this one let me call the second term, and this one let me call the third term, etc. Okay, so I'm going to write it up individually. So our response, and look at this template, and so that template becomes is the magnitude of the force divided by the spring constant, and which is Ke. And here I use these notations. Okay, Ke, Ce, Me. So for the first term, right now I'm working on the response to the first term. For the first term, the magnitude is F now divided by 2. Okay? And then that is 1 minus R squared plus 2 zeta R squared. And for the first term, R equal to how much? The first term is actually the operation frequency omega equal to 0. So this one is 0 divided by omega A. That is 0. Okay? And then here, let me take the cosine terms. So cosine, and that is the working frequencies, omega t and minus phi. So here, the working frequency equal to 0. So simply, that is 0. And what is phi? Let me call the phi 0 here. Phi, the template is arctangent that one. So arctangent 2 zeta r, 1 minus r squared. So here you simply take r equal to 0. We calculate it here. Okay, so r equal to 0. So that is the response for the first step. You good? So now we work on the response to the second term here. So simply we take the same template. So again, that is a magnitude. The magnitude of the second term is 2f now divided by pi. So that is a force. The magnitude of the force divided by the k here. So that is a spring constant, which is k. Okay, And then here the denominators, the same template, 1 minus r squared plus 2 zeta r squared. So now we work on the r. So r equal to, for example, this is the second term. Let me call this is r2. Okay? And what is r2? R2 equal to the working frequencies, and which is omega here. Okay, for the second term, its working frequency is omega. So that is omega divided by omega n. Okay, and then multiply with cosine and omega t minus phi2. So here the phi2 equal to arctangent 2 zeta r 1 minus r squared. So for this case, r equal to r2. You okay? Any questions? And let me know. We can get into details. So then you can repeat for the third term. The third term, you know the magnitude equal to this one. So get this one into the form F1 or F2. That meaning the magnitude of the force component. Okay, and for the third one, the working frequency is 3 omega. Using this number to determine R. R equal to whatever the working frequency, for that case 3 omega and divided by omega n. Then repeat the same template. Okay? And here for this one, because we expanded and in terms of cosine, so basically here for the response, we take up the same harmonic form cosine, and then we insert the phase lag here in terms of this form here. Okay? Good? And for every single term here, that is based upon our learning understanding from chapter 3. Okay, so basically the hinge for you to completely understanding here is we decompose the periodic force into the combination of the many harmonic terms. To each harmonic term, that response is like this. And this is based upon the chapter 3's learning outcomes. So the hinge for you is this. If you need more exercise about this one, simply go back to chapter 3, either our slides or the textbook, understanding what meaning of individual terms here, and then you simply do the linear combination superposition of the response. Okay, so that's for this example here.